So, first of all, I'd like to thank the organisers, Henri, Edouard, and Julio, for inviting me to speak at this conference. It is, I think, nearly 30 years ago that I was last in Saclay. And it's very nice to be back. It brings back a lot of memories. And it was my first postdoc was here in Saclay, and I arrived. I guess I was about 24 years old and rather new to research. And Serrano adopted me pretty much straight away, and I was very much energized by his enthusiasm for physics, and in particular for replicas and all the interesting things you can do with replicas, and also for his enthusiasm for very long calculations. I also picked that up, and I still haven't quite got rid of it, but I probably never will. So the talk this morning is probably one that would be of interest to him, which is to look at questions of what happens in replica symmetry breaking when you have take into account finite size corrections. And there's clearly been a lot of work done on looking at fluctuations about Parisi's scheme for breaking replica symmetry, and this is one avenue for looking at that. Okay, so I'll first of all start just a reminder of the model that we've got in mind. Here's the Sherrington-Kirkpatrick model of a fully connected lattice, and you have some disorder variable J, quench disorder, and some dynamic variable sigma, in this case Ising spins. And obviously there's been a huge amount of work on understanding this system. It shows very rich behavior. And the focus for what I will talk about today is one aspect of that, which is to do with the order parameter, or the generalization of the concept of an order parameter for this type of model. So in this case, what we know is that phase space is broken up into a set of free energy valleys, or pure states. And if you want to understand the system physically, you look at it trapped in one of those pure states. If you want to really understand what's happening, you can look at overlaps between those pure states. And one way of doing this is to just look at the overlap between the magnetizations in the two pure states A and B. And one way of capturing that, or part of the information from that, is to look at this P of Q, the distribution of those overlaps weighted by the Boltzmann weights that you get from the pure states. So P of Q is the thing that I will be focusing on calculating or looking at in a number of different systems. And if you do replicas, P of Q seems to arise as some obscure but very exciting sort of picture of the world. But the nice thing is that you can actually simulate it directly. This is work that Peter Young did in 1983. I remember seeing this when it first came out and being very intrigued that it was possible to get direct access to something that was generated using replicas. And the way you approach this is you take two identical copies of the GIJ, and you can define the overlap between those two copies. You simulate them, and you track that overlap over time, and that gives you an estimate of the distribution of overlaps. And on this picture you can see that you get, this is the thermodynamic limit, the large system result, which is you get a delta function peak here with a smooth curve down here, and you can see that there's significant finite size effects. And this is still an area being worked on. This is fairly recent data, taking this up to about 4,000 sites. And you can see the way the the delta function peak, which we assume it is, narrows. So I assume doing this particular simulation probably took many hours of supercomputer time. I don't know. But this looks rather similar, and it took 2 minutes on my PC last week. This doesn't reflect an improvement in computer power. It's just that this is a much simpler model, which I'll explain how it works later on. But this is a direct calculation of the overlap in a problem where you get replica symmetry breaking. But because of the nature of the problem, it's very, very easy to obtain numerical results for P of Q. And these are strictly exact for different sizes of system. In this case, you construct the system as a tree, and these are simply the heights of the tree that are increasing. So you can see as the height of the tree increases, you get a greater peak. And I'll explain how this works later on, but I just thought it was interesting to see the sort of thing you can get from it. This is also some recent simulation on 3D POTS glasses of P of Q. And the assumption is that in the thermodynamic limit, you've actually got two delta function peaks, and that this effect in the middle is a finite size correction. And why does it do that? Do you answer, John? Okay. So yeah, so this is again going back to the much simplified model that we've been using, and this again looks at a system that has two delta function peaks, and we compute the finite size correction between that peak. So I've actually cut off the delta function peaks here and just shown directly the finite size effect in the middle. And this again increasing size of the tree here, and then the thick line is an analytic prediction of what happens in the thermodynamic limit. And we find this structure here, which it probably applies to a large class of problems where the overall finite size effect goes as 1 over root n, and then you get q times 1 minus q to the minus 3 over 2 is the shape of the curve. Okay, so that's kind of just a brief introduction to the sort of things that we have been looking at. So the main focus for the talk is to say, okay, we have the replica method has generated some very valuable results in the thermodynamic limit. It has been proved quite difficult to make predictions beyond a mean field n goes to infinity result. And we've extended that. What we find the two main findings are that there are a set of things that I'll describe which are shifted, but in a well understood way in terms of replicas. So you can see how you need to look at fluctuations about the replica solution to get the results. And then there is a separate class of, in this case, one-step replica symmetry broken problems where you get this finite size correction that goes as 1 over root n with a particular form. And there it's actually very difficult to see how a replica calculation would generate that. That is not to say that it won't, but it is not immediately obvious how that would be generated. We certainly don't understand at the moment. So what I'll talk about is, first of all, a quick review of replicas and finite size corrections. Then I'll talk about the random energy model as probably the simplest case that we can look at. Then the polymer on a random tree, which is what gave the results I talked about earlier. And then finally, if I have time, talk a bit about the generalized random energy model. Okay. So with the replica approach, the first step is really to deal with the log by introducing n replicas of the original system. You can then, with a lot of work with Gaussian integrals, convert that to something where your order parameter looks like a coupling between pairs of replicas, Q alpha beta. You then can look at fluctuations about the saddle point Q star, and you get something of this quadratic form. And this is where you would expect to be able to see things like finite size corrections. And it becomes very hard because you want to take n goes to 0, so you need to have some sort of analytic continuation. And so far, as I know, there are very few examples where you can really make sense of that in terms of estimating finite size corrections. One example from Campoloni, Parisian, Versoro in 2010 was to look at the p-spin model, so the p-spin generalization of the SK model, in the large p limit, which is, all you have to do is one-step replica symmetry breaking. So you take your n replicas, split it into R blocks of size mu, and they guessed that by looking at fluctuations in that block size mu, you would be able to estimate the finite size corrections. And the nice thing about this is, because it's a random energy model, there are other methods you can use to find those finite size corrections exactly. So you know whether you're getting the right result or not. They made some clever assumptions about which saddle points would actually contribute, and showed that with those assumptions you can obtain the correct finite size corrections. Now, so that's really the only example I'm aware of where some serious progress has been made with this. So now I'll talk about the approach that we've taken, which is certainly for the random energy model related to what Campoloni et al. Did. Now, for the random energy model, the concept is for any sort of SK model, you can compute fairly easily the distribution of energy levels. So here you've got the ground state, you've got some low-lying energy states, and then you've got a continuum of energy states. And the spin glass phase is dominated by what happens down here. Now, obviously, for something like an SK model, these are strongly correlated. And Bernard made the interesting assumption that let's just take these as being independent random variables, and you get something called a random energy model, which displays many of the interesting features of much more complex spin glasses. So in the work that Bernard and I have done, and this was 2015, we looked at a somewhat simplified version of the random energy model. Simplified in what it made the calculation simpler. It's actually harder to explain. But effectively, you use a Poisson process to generate that distribution of energy levels. And you have an exponential term which actually is enough to determine the behavior of the low temperature phase. And then a Gaussian term, an epsilon here in all of this will be 1 over the size of the system. So that's your finite size effect. B I'll actually take for 1 in this case, but it comes back later. So for this model, there are methods to compute exactly the finite size correction. But it's also quite interesting to look at how you approach it using replicas. So obviously the replica method, you have z to the n, you're basically taking n copies of what in this case is a very simple system. And if you just apply the multinomial formula to this, and then you take the averages on these independent energies here, you get something that looks like this, which at first sight is somewhat complicated, but really all it's saying is you've got a Kronecker delta here, which constrains these mu I add up to the number of replicas. And it just goes through all the possible ways you can split those replicas into R blocks. And this function psi is very easy to compute in this case. It's just something that goes as e to the n with a fairly simple quadratic term here. So we know with replicas how to solve that problem. All we do is assume that the term that dominates that sum just has all the mu I the same. So that is what's going to dominate the sum. This gives us the leading term of this form, and indeed it gives you what you know to be the correct thermodynamics for the system. And the mu, which is the block size of replicas, is 1 in the high temperature phase, so there's just one block. And then in the low temperature phase, its mu is T over Tc. So it gives you a very simple spin-glass phase. And there you're getting one-step replica symmetry breaking. In which case, so in this case, the P of Q that we wanted to calculate is simply two delta functions with, and because of the construction of the random energy model, either the overlap between two states is 0, 1. They're either the same state or different states. There's only two possibilities. And here, the weight of these delta functions is P of 2, P2, which we define to be the probability of finding two copies of the same sample in the same state. So it gives you a very simple picture, but if you looked at something like the Potts model in 3 dimensions with, I think, next nearest neighbor coupling as well, it basically is of this form. So this is telling you quite a lot about how a spin glass would behave. Okay. So I'm not going to go through how you do exact calculations on things like the random energy model, but I think it's quite instructive just to look at the basic difference between replicas and the exact approach. And if we generalize P2 to what I would call Pk, which is the probability that k copies of your system are all in the same state, which is just given by this quantity here. This is the Boltzmann weight, it's about k, and then you sum an average, which will give you the probability. Now, in the replica approach, you face the problem of having z in the denominator by taking z n to the minus k, and assuming n is greater than k, and you get back what you want, and the n goes to zero limit. So it's a question of how you bring this out of the denominator, which then it gives you the correct result, but creates a lot of interesting problems with what does n mean when it's not an integer, a positive integer. So the alternative approach that Bernard developed for the random energy model is to use this gamma function integral, and so I can actually express, as long as k is positive, I can express it in this form. And so my z, rather than appearing back on top, is actually appearing in this exponential here. And when you take the average, you have this generating function, and it's very easy to, in the random energy model case, to do the average simply because you've now got z in the exponent. These all separate out. You can do the full average. And that's why, to then do calculations after that is a lot of work, but basically that's the two alternative ways of approaching these types of models. So there's a class of models that you can use this approach for and then compare it with the replica approach. And the common characteristic is in some way you can decouple this z into a series, either one product or a series of products at this stage, which is why you go for models on a tree. Okay, so after lots of hard calculations that Serrano would have enjoyed, you eventually get, using these exact methods, an expression for P of k, which is all based on this structure here, which in replicas is very easy to obtain, and it's basically comes from the combinatorial factor of how you choose replicas out of blocks. So it depends on how you choose. If you work out the combinatorial factor, you get a series of factorials. You convert those to gamma functions, you take n goes to 0, and you always obtain this sort of structure if you're looking at the probability of k replicas being, or k copies of the system being in the same state. And then what we see here is the 1 over n correction. And what we've managed to do is re-express this as the first and second derivative with respect to mu, which is the block size, of this expression with some higher order terms. Now obviously these expressions are very complicated, but from a replica point of view, you can see immediately that if it is of this form, then you can think of this as a shift in mu, and this is a fluctuation in mu. So it becomes very clear for this sort of problem that the replica approach, if you look correctly at fluctuations in the block size, you will indeed be able to predict the correct finite size corrections for P of Q. So there it looks, it's a nice way of approaching the problem. Now, the work that Campoloni et al. Did showed that if you make correct set assumptions, you can indeed get these results. We found Bernard and I found a different way which basically mathematically looks the same as what Campoloni did, what we call complex replicas, but it's actually a reformulation of the exact approach. And you get nice effects, as Campoloni observed, which is that as you move into the complex plane, the fact that you get this saddle point, so minimas become maxima in the replica method, is simply a fact that you've now got a saddle point in the complex plane. And so the shift from maximum to minimum, it reflects that. So the exact method in this case, and it's not clear whether you can generalize it to other types of models, but it works in this case, that you can see how that arises. Okay, so that is the simplest model, what we call the Poisson random energy model. Now I'd like to talk about the binary tree. And what I mean by that is you have a tree that just, regular tree that splits with a branching rate of 2, and you associate the configurations with the endpoints of the tree, so each path down the tree gives you a configuration. So this is T is what we use for the size of the tree, T equals 4, gives you 16 possible configurations. You then associate a random energy with each of the bonds or edges in the tree. So you can use an arbitrary distribution for this. In the numerical results that I talked about, we use a very simple distribution where the energy is either 0 or -1. But yeah, you can actually extend it to have this different for each level within the tree. So if you want to compute the energy, then the energy of each of these configurations you can compute by just adding up the energies associated with the bonds. And what that means is we now have correlations between these configurations. So if we think about the overlap, obviously there's no spin configurations directly in this model, but you can quantify the overlap in terms of how correlated two configurations are, and that depends on how many links they've got in common. So here the overlap is defined as 1 over 4, because 1 out of the 4 possible bonds they actually have in common. So a nice way of defining the overlap. And you can again calculate P of Q for this type of problem, where you've got the usual Boltzmann weights. Now, these, how do I go back? No. How do I go back? Page up somewhere.
The arrows?
No, I tried the arrows. Let's try that one. Is that going further or going back? Okay. Oh yeah, that's what I want to do. So yeah, sorry about that. So here, what is clear is that you've got your large tree here, you've got these two trees here, these are completely uncorrelated. So, and you've got energies associated with this and this. So you can think of a sub-partition function for this and for this, which then immediately gives you a recursion for the partition function. So you can relate the t+1 tree to the two separate t-size trees. And as we did with the random energy model, you get a generating function. And here, that what I've got is a slightly different way of expressing it, but it's basically the same structure. But now, rather than having a simple expression, here you can use the decomposition here, the fact you can look at two separate trees, to generate a recursion for the generating function. And obviously, when I assume that the epsilon can either be 0 or -1, I get a particularly simple form for that. In addition, the equation that it's satisfied is of an FKPP type, which Bernard talked about yesterday. So you start with some initial G0, you end up with some final GT for your tree of size T. And interestingly, the free energy of the system is just the area between this curve and this curve. So the envelope gives you the free energy. So it's a very nice relation between something that looks completely like a spin glass and you get to a traveling wave problem. So the extension, this work was, the work on that was done in the late 80s and early 90s. This is the way we've extended it, is to say, well, we can again look at something like the Q2 or P2 that we talked about before. Here we call it Q for some reason. Previously called it P. I'll actually change it. Well, I'll come on to that. There's a slight complexity in notation here. But this is the probability that two copies of your system have an overlap of R or more. And you can express it in terms of this function H, which again satisfies a recursion, so on the tree. And to leading order, H looks very much like the derivative of G. So if you think about the derivative of G, it basically looks like something a bit like a solitary wave moving in this direction. And the area under that gives you this estimate of the probability of overlap of two replicas. And you can generalize this in various ways. And that, by numerically solving that recursion for G and then for H, we can then get our estimate of P of Q. And this then gives you the finite size corrections with the dashed lines here for the different sizes of tree. And this, what I come on to, is our analytic prediction of what the infinite size system would look like. How am I doing on time?
You have 15 minutes.
Okay, that's good. Okay. So now what I want to do is talk about how we approach this. But I'll take a slight detour, an interesting detour, to talk first about the case where you're looking to go. We've talked about two models where you had one step of replica symmetry breaking. Now I'm going to talk about where you can actually add as many steps as you would like of replica symmetry breaking. So in this case, what you do is you still have some distribution of the energies, but you want to introduce correlations. And we saw with the binary tree how you can introduce correlations between those different states. And this generalizes that concept by having a different distribution at each level. But we again, for simplifying the calculations, we again use the same trick we did with the Poisson random energy model, where it's actually a Poisson intensity. So it's the points of the Poisson process at each level, and you just have a hierarchy of these Poisson processes which generates your tree, and therefore your correlations. So you get something like this, where you've got a varying branching rate, but you can in the end simulate pairwise correlations of whatever form you want. So you can get the same pairwise correlations as the SK model, for example. But otherwise it's exactly the same as a binary tree. You simply generate the energies of the leaf nodes by summing the energies you get down the branches. And the reason you can solve this model is because you can now take the limit where you've got a very large branching rate. And the reason you can, which I'll come on to later, the reason you can use this to approximate the binary tree is if you imagine a chunk of binary tree which, say, has got 2 to the n or 2 to the m points at the bottom, you can just map that onto a single level within the tree, this form of tree. So you can make a mapping between the binary tree and the generalized random energy model. So very much the same way as the binary tree, you can define exactly the same type of generating function. You obtain a slightly different recursion down the tree. The temperature, as in all these tree-like models, just comes in through the initial conditions. So this gives you basically the curvature of the initial slope, the initial wavefront gives you the temperature. And in the first case I'll talk about, where you can introduce as many replica symmetry breaking steps as you want, is where the parameter A, if anyone can remember what A was. I think I've got it, yeah. So A is, in the low temperature phase, A pretty much determines the thermodynamic limit behavior of the system. So I can choose those. So if I choose those so that I get they also determine obviously transition temperature. So I choose them so we get a sequence of transitions, and I assume I'm in the lowest temperature phase. So I've now got, in this case, Tor steps of replica symmetry breaking. And very much like the random energy model, I can compute the probability that k replicas, or so k copies of the same system, have an overlap that is greater than the number here. The notation gets slightly complicated, but you see it's exactly the same form where you've got this combinatorial factor which comes through replicas. If you did this calculation for replicas, you would see that it was choosing replicas from blocks, and then it's actually the A for the overlap point which gives you the value of Z to use there. But the key thing is you get the same shift in your block size, and you get the same fluctuations in your block size, but the expressions are somewhat more complicated than they were before. So again, it seems that in this case where you've got a finite set of steps within your replica symmetry breaking, it's reasonably clear how you could adapt the replica method to give these sorts of results. Now, obviously, there's a lot of work in actually being able to do that, but at least it looks as though it's of the same type, but with a shift in the fluctuation. So one way of thinking about this, and this is where I was talking about the notation, in the original literature, so Mazar et al. In 1984 introduced this expression yk, and this is actually equivalent to what we've just been calling qk, unfortunately. So it's again the probability of having k copies of the system in the same state. And from the replica method, you get this relationship between yk with k greater than 3 is basically dependent only on y2. So you get all the structure of yk simply from a function of y2, where this is the familiar structure that we've seen a number of times before. And basically what we're saying in these models, if you allow for a fluctuation in the block size, which is unfortunately negative, so the variance of that fluctuation is negative, then you will get the correct finite size behavior. So it shows that in this case you can see how replicas would generalize to these problems, at least in principle. So a different problem, which is, how much time have I got?
You have 10 minutes.
Okay. So yeah, this I will not go into too much detail on, but in the binary tree case, we wanted to be able to estimate the P of Q, the finite size correction for the P of Q. And the way we do that within the GREM is to assume that all these A's are equal, which creates an interesting problem in the way you calculate it. But the key thing within this, I won't explain in detail, but effectively the shape of the wavefront is determined by this function f, small f. And it has a very simple recursion, which is effectively, it looks like a Brownian motion in discrete time. So you've got your initial condition, F1 gives you this Gaussian distribution, and then at each step you allow a jump which is based on a Gaussian. The only interesting thing is that you're restricted only to positive values. So it's a constrained Brownian motion within discrete time determines this. So this connects back to what Bernard talked about yesterday. Effectively, you've got some, as you go to very large trees, you have some path, Brownian path, which is constrained never to cross this line. And that determines, if you follow it through, that determines the structure of PQ. Sorry, that I need to slightly ahead of myself. So this gives you the structure of G and therefore of the free energy. If you look at the generalization of the H that I was talked about previously, which gave you Q of K, the corresponding thing here is you're constrained that at some point in the path you actually touch the side of the triangle. So you have a kind of doubly constrained path. And this is what gives you the structure for P of Q. So the finite size corrections come from that. Whoops. Probably ought to go to the next one. Yes. So that what I just described gives you this estimate here, the full line. And what we see is this is the structure that I just talked about, P of Q. It depends on Q in this power of 3/2. What we haven't done is, if you look at the replica view where you get this sort of factor, this, because we've only calculated the first term, it only gives you a shift in the block size. So it's not clear within replicas how you would obtain that.
How is this normalized when it's not
So here I've rescaled it with root t so that they all lie on the same curve. So you can, there is a normalized version if you want to look at that.
There's a cutoff for Q to 0 and 1?
So, oh yeah, so if you look at this, yes. So here, I didn't actually put it down, but effectively Q has to be sufficiently far away from 0 or 1 for this to be valid. So it scales to the size of the tree is what you require. Okay. So the conclusions are, as I showed, that some in the models we looked at with the random energy model or the generalized random energy model, where you've got a finite set of steps of replica symmetry breaking, it's reasonably clear that if you look at what we call fk, which is just a function of y2, which gives you all of the yk, as in the usual replica approach, then there's a fairly simple way to modify that, which you can think of as a fluctuation in the block size. So there's a reasonable way of seeing how you would adapt the replica method to give those types of results. There's also this case where, again, even if you're just looking at a problem with one step of replica symmetry breaking, you've got two delta functions in P of Q. The finite size corrections have this rather interesting form where it depends on root n, but with a particular structure for the dependence on Q. Okay, thank you.
Thank you very much.
When you're computing these finite size corrections, you're really doing an interval by steep descent. And so, if the eigenvalues for Hessian are finite, it would seem natural to expect that correction would go like 1 over root n. But in the SK model, where there are massless eigenvalues, would you still expect this 1 over root n dependence there?
That I'm not sure about. So I guess my answer to that would be that I simply don't see how you would get this form using the replica method in this case. So whether it applies in the SK model, I'm really not sure. So, and people have reported other similar behavior since in related models, but nothing that looks like the SK model.
There are other questions. I have a question and a comment myself. Actually, in the one-step replica symmetry case, we know in replicas that there are two kinds of replica symmetry. One step. One which is continuous, in a sense in which there are zero modes that
Yes.
Mike was alluding to, and this is this case here. And there is another case which is discontinuous, there are no zero modes. And in that case, rather the P of Q has the form of a large deviation function exponential of minus n times a function of Q. And this is something that we are able to compute with the replica method. Now, I think that the case that you are looking at of the binary tree with all equal A's
Yes.
is right, the marginal case. If you reverse all the inequalities that you have for the continuous transition, how do you call it?
As simultaneous. You mean
No, you have the gradual and the simultaneous.
Yes.
So if you reverse all the inequalities that you had in the gradual case,
Yes.
then you wouldn't find a 1 over root n, but you would rather
Yes,
find the exponential of minus n.
Yes. Yeah, I think this is true. Yes.
Other questions? No, let's thank again.